Hey guys, welcome to module 3.3 of this Learner Space course on device physics. Today I want to talk about semiconductor dynamics. So last module we spoke about carrier concentrations and how the semiconductor is when you just leave it on its own in a cupboard. Today we want to talk about when things are actually moving, when you have voltages, fields, when you have like non-equilibrium situations, how do we analyze the dynamics? And once we develop the equations for this, then we can apply it and use it to understand any device. Cool, so let's get into it. So the stuff that we're going to cover in this module, uh, firstly we're going to talk about drift, then generation and recombination, then diffusion, and then finally we're going to use all these concepts to develop the equations that govern these dynamics. We have a set of four equations called Shockley equations, and we have Gauss's law, which you've probably seen before, but we're going to apply it here as well. Cool. So first thing I want to talk about is drift, right? So here they've given like a normal band diagram which you have in equilibrium, which is something we've seen so far. If you have an N-type material, your Fermi level is likely to be somewhere near the conduction band. If you have a P-type material, it's likely to be somewhere near the valence band. This is something we've seen before. And the intrinsic Fermi level is roughly between the conduction band and valence band, almost accurately. Right? Now we're going to talk about the case where, say this is your semiconductor material, you pick it up and you put a battery across it, where there's a high voltage on the left side and a low voltage on the right side. What that's going to do is it's going to create an electric field from left to right. Now, one important thing to note before we get into how the band diagram looks is that if you go back to when we learned about the energy band diagram, we spoke about how it represents the energy of the electrons. So, uh, now we know that electrons move in the direction opposite to the electric field. So it's obvious that when you have any field, things move from the direction of high energy to low energy, which means that if you have electric field in the right, you need because of which electrons move towards the left, the electrons have lower energy on the left than the right. And since energy, like we are literally plotting the potential energy, we know that the potential is the integral of the electric field. So if we have a constant electric field, we will have a linear energy profile, right? So this is why all our bands slope upwards in the direction of the electric field because they represent the energy of the electron. So the electron has a tendency to move from right to left, which means the field at the left is low and the field at the right is high. So this is how our bands change in this direction. This shows the flow of electrons from right to left. Obviously, holes will flow in the direction of the electric field because they behave like positive charges. So they'll flow from left to right. And overall, the electrons as well as the holes will contribute currents. And we are talking about the current per unit area, which we represent by J. So Jp is the current due to the holes, Jn is the current due to the electrons, and J is the net current. So when you have this electric field that causes these currents to flow, this type of current is called drift current. Cool. So, just getting into the physical significance or meaning of drift current. So, in the absence of electric field, you have these electrons making random collisions moving in random directions, right? They make random collisions with the lattice and keep changing the direction. Because this is random, there is no net current that is caused due to this, but the electrons keep moving around. Now, when an electric field is applied, Obviously, these random collisions continue, but there is some net movements of the electrons in the direction opposite to the electric field. So if you follow a given electron, its like movement might appear random, but when you actually like follow it for a significant amount of time, you'll see that there is a bias in its random movement where it's slowly moving on net towards the direction opposite to the electric field. So that is how drift current works. So just some like more mathematical look at drift current. So this is just our expression for Newton's law, right? Mass into acceleration is the force in an electric field. Uh, Now in this we have in due to the lattice we have a lot of scattering. So when we add this term of V by T or V by tau, this V by tau like talk it basically represents or models the friction due to this scattering. So this is the differential equation we have to solve to actually get V, right? And our this what you see represented by tau m is actually called the mean time between collisions. So this V by tau is kind of just representing some type of frictional force that acts on this, right? And like if you rearrange this and write it according to Newton's laws, you'll see that that term comes out, and you take it on the right hand side, that comes out to a force of minus mv by tau. And because tau is the collision mean time between collisions, and before the after the collision it has zero speed, before the collision it has speed v, so the average force that this friction, quote unquote friction, creates is minus mv by tau, and that is something we can rearrange and develop this equation. Now, we are interested in what is the steady state drift, right? Because ultimately things are going to take the steady state, and in some sense the average is going to give us the steady state. So in the steady state, we assume that the acceleration is zero because you have steady state conditions, and you directly equate the drift velocity upon tau to this q e by m, and this gives us an expression for this drift velocity. And this term q tau by m is what we call the mobility. So we basically get the drift velocity as the mobility times the electric field. Now finally, a direct consequence of Ohm's law is that you have the current per unit area as directly related to the drift velocity. You can like look at how this expression comes in any like class 12 physics textbook when you talk about current, but even intuitively the current is going to be proportional to the average drift velocity or the speed at which the electrons are drifting. So this is the expression that we get for that, and so we are also able to see how the current you get a current that is proportional to the electric field. Q here, of course, represents the electronic charge. So the same way that we can like write the current due to electrons, we can also write the current due to holes. And finally, this is the expression we get for the net current. Uh, all this can be derived directly from Ohm's law. So it depends on the number of electrons, the number of holes, the mobility of electrons, and the mobility of holes. And of course, the electric field, all of which is what we would expect. And it is this term that we in fact call the conductivity of the material. So this equation is sometimes written as J equal to sigma E, which is another form of representing Ohm's law, where sigma is the conductivity. So yeah, this is just some mathematical treatment of drift for you to keep in mind. Cool. So now we're going to talk about a different phenomena, which is called generation. So what do we mean exactly by generation? We mean generation of electron hole pairs. And just intuitively, if you have lot of electron hole pairs getting generated, this can have a big effect or impact on the dynamics of the semiconductor, because like you suddenly get a lot more carriers, right? So it can occur in many ways, and it is caused mostly due to external factors outside of the semiconductor. So I'll give you an example application, which is a solar cell, which works on this phenomena of generation. Now, what is the purpose of a solar cell, right? The purpose of a solar cell is that we want to convert the light energy from the sun into electrical energy to power our motors or generators or anything in general, right? So that's the purpose of a solar cell. Now, how does the solar cell actually go ahead and do this? So photons from the sun will fall on the semiconductor material, and the atoms at which these photons are falling, it causes the generation of many electron holes pairs by displacing an electron from an atom in the lattice, which will create an electron, and from where the electron was displaced, a hole gets created. So when you have these light rays falling on the semiconductor material, you get electron hole pairs, and in this solar cell semiconductor material, you keep a fixed electric field from before. You keep it applied. The moment these electron hole pairs get generated, they will flow due to this electric field, which basically means you are getting some type of conversion from light energy to electrical energy. So yeah, this is how a solar cell works. This is how we leverage this concept of generation. uh, we represent the rate of generation by G. So essentially what G represents is the number of electron holes pairs generated per unit volume per second. That is what G represents. Cool. On to the next phenomena, which is recombination. So just like you can have electron hole pairs spontaneously generated, these electron hole pairs can recombine with each other also. So to give some intuition for this, imagine like our solar cell application or any similar application where you put a strong pulse of light on a semiconductor for 1 second, and then this pulse of light goes off. Obviously, this will create a lot of excess electron hole pairs over and above what are present in the equilibrium. Now, eventually for this semiconductor material to attain equilibrium, these electron hole pairs must again recombine with each other. Now, what we are interested in is what is the rate of this recombination. Now, what we are going to claim is that the rate of this recombination is some constant times the product of electrons and holes minus the product of electrons and holes at equilibrium. Now, the motivation for this comes from something you would have seen in chemistry, which is called the law of mass action, where they basically tell you that a rate of any chemical process is proportional to the concentration of the reactants in that process. So this is like a more statistical or probabilistic law, or it's something that you can apply to a large number of things, right? Like even in nuclear reactions, you talk about the rate of decay being proportional to the number of things. So anything where you have something that happens probabilistically, the more the number of things you have, the higher the likelihood that some of them will recombine, for example, which is why we expect it to be proportional to the number of electrons and the number of holes. Now, why we have this offset of the product at equilibrium is because when you have equilibrium, when N is equal to Ni, the concentration at equilibrium, and P is equal to Pi, we don't expect there to be any recombination because that is the definition of equilibrium, right? So we expect that over and above equilibrium, whatever product gets created, due to that you have some rate of recombination. So based on this argument of this law of mass action, we get this rate of recombination as some constant times Np minus the product of Np at equilibrium. So this is how we intuitively see the rate of recombination. Cool. So let's like further develop this. So let's assume that we have initially p-type doping. We want to now talk about some approximations where this formula becomes cleaner. So if we have p-type doping, then at equilibrium, your like number of holes is going to be much larger than the number of electrons. After your excess carriers get generated by whatever process we're talking about, like we spoke about a pulse of light just like hitting for 1 second, right? Then obviously you have like Ni plus delta n electrons because you have those many electrons generated, and you have Pi plus delta n holes as well. And the reason why we have delta n in both of these is that electrons and holes are generated as pairs. So for every excess electron you get, you also have an excess hole. Now the assumption that we are going to make is that this delta n, since you have p-type doping, delta n is much smaller than Pi but much larger than Ni. And this is, of course, the result we're going to derive is going to only be true under this assumption. But this assumption is quite common to make because we already have that the number of holes is a lot larger than the number of electrons. And we see when you see orders of magnitude, this will be of the order of 10 power 15, this will be of the order of 10 power 5, for example. Then for delta n to cross P or be smaller than Ni is very rare. So this approximation holds in a large number of cases. Any which way, so we're going to solve using this approximation. Now, if you substitute this value for n and p in the equation we had in the last page, uh, and you apply this approximation, what you're going to get is that your rate of recombination comes as C delta N. And we replace this constant C by some constant 1 by T. So we write the rate of recombination as delta N by T, and we call T the minority carrier lifetime. The reason it's called the minority carrier lifetime is that this condition of delta n being bounded in this sense is called minority carrier injection because you have like a lot more p than n, right? And the moment you have generation recombination, you're going to have equal generation of both electrons and holes. So on net, more minority carriers are getting injected. This is why this phenomena is called minority carrier injection, and T is called the minority carrier lifetime. Again, these are just names. It's not that important. What's important is to see that this rate of recombination is proportional to the number of electron hole pairs you generate under this approximation. Now, like just to be clear, minority carrier is just the carrier, be it an electron or a hole, which is less numerous. So if you have p-type doping, your n-type carrier becomes a minority carrier. Cool. So this is the expression we have for recombination. Let's get into diffusion, right? So diffusion is the transport of particles due to a concentration gradient. So if you have a semiconductor material, there are a lot of electrons on one end of the material and almost no electrons on the other. Obviously, there is going to be transport from the low concentration side to the high concentration side. Now this happens purely due to the thermal motion of electrons. So by the random nature of the thermal motion, particles are going to tend to move in a direction where there is less concentration. So what's basically gonna happen is that electrons are like moving randomly in thermal motion, right? Imagine you like you just take a semiconductor, you have like a lot of electrons concentrated on one side and none on the other side. If these electrons, even if they start moving randomly, slowly they're going to like move and occupy the whole material, right? Just like how you spray a perfume on one end of the room and all its particles eventually spread throughout the room, even though they're moving just randomly, is the same phenomena. So diffusion is just movement due to a concentration gradient. And we basically we can just write the diffusion as being proportional to the concentration gradient. So if you have a lot of electrons on like one side and less on the other, then proportional to the gradient you're going to have diffusion. E is just the electron charge, which is of course intuitive that your diffusion current is going to be proportional to that. And D is just some constant which we call the diffusion coefficient. So intuitively this formula also makes sense. And one last thing is that we can have diffusion of both electrons and holes. So just like you're going to have diffusion of electrons from high concentration to low concentration, you're also going to have diffusion of holes. So you have both these diffusion currents. So I've spoken now about drift and diffusion individually. Now I just want to like help you derive the combined expressions for drift and diffusion. So for that derivation, just setting up the context, there is an electric field that goes from left to right. As you all know, the drift current is due to the electric field. So the electrons will drift in the opposite direction of the electric field, the holes will drift in the direction of the electric field. And we've basically come up with a concept of representing the flux because the flux represents the direction in which the carrier moves. So we are going to represent the direction of the flux, and we know that for electrons the current is going to be opposite to the flux in which they move, and for holes it's going to be in the same direction. Cool. So this is the electric field from left to right. And as you know, for the diffusion current, it's due to a concentration gradient. So things move from high concentration to low concentration. So here we have represented the concentration. So as you can see, as you move from left to right, the concentration of both the electrons and the holes is reducing. So we have set up this context. Let's now analyze on the basis of this context the directions of the various fluxes and currents, right? And then we can then come up with these expressions. Cool. So we first start with the holes. So we know that for holes, you're going from high concentration on the left to low concentration on the right. The diffusion current is going, the diffusion flux is going to be from left to right because holes want to move from high concentration to low concentration. So this is why you have diffusion flux in this left to right direction. Now, the holes also experience drift due to this electric field, and because holes are positively charged, they will move in the direction of the electric field. So the drift flux is also left to right. Now for holes, the current is going to be in the same direction as the flux. This is because the flux is basically from like the positively charged particles move in the direction of current. So because current is defined for positive charge, right? So we are going to have diffusion also from left to right because the diffusion flux is left to right, and we are going to have drift also from left to right. What this basically means is that your drift current is very clearly positive because it's in the direction of the electric field, and your diffusion is in the direction where dp by dx is negative. So you will put a minus sign here, and this gives you the net hole current. So yeah, the reason you put a minus sign here is because they're both adding up from left to right, and we know that dp by dx is going to come negative. So if we want this diffusion term to add up, we'll put a minus sign here. So this is the derivation for the holes. Let's get to the electrons now. In terms of the diffusion flux of the electrons, electrons are also going to want to go from high concentration to low concentration, which means that the electrons are going to flow from the left to the right. So this gives you this diffusion flux. In terms of the drift flux, we know that electrons in terms of drift are going to go in the direction opposite to the electric field, which is means they are going to flow from right to left. So this is the flux of the drift, right? Now, for electrons, the current is in the direction opposite to which they're moving, because current is defined as positive for positive charge. So if electrons are moving from left to right in diffusion, the diffusion current is going to be from right to left. And similarly, if electrons are moving from right to left in drift, the drift current is going to be from left to right. Using this, we can clearly see that the drift current comes positive and the diffusion current comes negative. So we have a positive drift current, and because we want this whole term to be negative, and we can see that dN by dx is negative, we will put a plus sign here to ensure this term is negative. So this is how we get the net electron current. So these are the net current expressions that we derive, and we can use this based on any context to basically write the current due to the electrons and the holes. And of course the net current is going to be because of the sum of the currents due to the electrons as well as the holes. So you've just combined the drift and diffusion formulas based on the directions in which things are flowing. Cool. So the next thing we're going to get into is this thing called Shockley's equation. Shockley's equations are a set of totally 4 equations which represent the dynamics of a semiconductor, and together combining them with Gauss law gives you all the equations that you need to represent any type of movement or flow in the semiconductor. Now, the first two Shockley equations are exactly the ones we saw in the last slide, the drift diffusion equations, which give us the net electron current and the net hole current. And that's basically the first two Shockley equations. And we have to now explore the other two. Then we'll have the complete set of 4 equations that help us describe things. So what do the other two equations represent? They represent the rate of change of carrier density at a point. So let's get into that. Cool. So let's get into these equations. Uh, we'll talk about the case for electrons, and the case for holes is just the symmetric argument. Now just don't get intimidated again by any of the symbols. We'll just get into it like term by term. So first let's look at the first term. The first term represents dN by dt. Remember that n is the number of electrons per unit volume. So just imagine a unit volume in a semiconductor. You have electrons in this volume. Now with respect to time, how are the electrons changing? The number of electrons in this given unit volume, how are they changing? Now, let's consider the ways that they can change, right? You have certain number of electron hole pairs already inside this unit volume. How is it possible for it to change? It's possible for it to change in 3 ways. Either it increases because of generation. So, for example, if there is some light that is being thrown here that's giving energy to atoms and that's creating more electron hole pairs, you can, due to generation, with respect to time, your number of electrons in this unit volume will increase based on the generation. Or it can reduce due to recombination. If some recombination is happening, that is reducing the number, or electron and hole are recombining with each other, which will reduce the net number of electrons. So this is the second way that the number of electrons can change with respect to time, because of the recombination rate. And final way that it can change is if the current that comes in is more than the current that goes out. So these are the 3 ways that this dN by dt term can change, and that is why we basically have this 3 terms. That is the representation of these 3 terms. The first term represents the gradient of the current, which is basically how much difference is there between the current coming in and the current going out. So and we divide that by 1 by e, because we don't want the like the total charge, we want the number of electrons. So we divide by the electronic charge. Now, so this is the first term which represents the difference in the current coming in and current going out, which can increase which can increase n. Second term is due to generation, and third term is due to recombination. So with these three terms, we get an expression for how the number of carriers changes with respect to time in a given volume. So we have the same expression for electrons as well as holes, and combining with the two equations on the last slide, we have now all four of Shockley's equations which we can use to describe dynamics. So now the next thing I want to do is talk about a condition that comes up quite often, which is steady state. So in what we mean by steady state is that the device has come to some state which is now it's going to continue to remain in that state. So obviously in steady state you're going to, for a given volume, your number of electrons or number of holes in that volume is not going to change. So this term is going to be zero and so is this term. And your rate of generation and recombination are going to balance each other out. So you're going to have this condition as well. And what that's going to give you in as a consequence due to the equation on the last page is you're going to get the gradient of the current as zero. What this essentially means is that the current is the same throughout the device, which is a really important result which we will use when we analyze devices. Because the thing is that if you analyze devices for steady state, if you're able to then like figure out what the current at any given point is, you can say that that's going to be the current throughout the device because you have these conditions in steady state. So this is an important consideration to make. Cool. Finally, what we're going to talk about is Gauss law, and this is probably something you have seen in JEE. And in JEE, you've probably seen Gauss law in the integral form, where you use the integration to find the flux and relate that to Q over epsilon, right? Uh, this is mathematically the same, but we use it in a different form, which is called the differential form of Gauss law, which is given by this expression right here. Here, epsilon is, of course, the permeability of free space. E is the electric field. They're saying that the gradient of this term is the net electronic charge in that region, small region around which you're doing this gradient. So uh, I'll just give the intuition for this. The intuition, okay, so first, before I move on to the intuition, let me just tell you what this net charge represents. E represents the electronic charge. P represents the number of holes, that's why it's in positive. N represents the number of electrons, that's why it's in negative. Na represents the number of acceptor impurities, that's why this term is positive, and Nd represents the number of donor impurities, that's why this term is negative. So overall it constitutes the net total charge. Now, why is this intuitive? Is that there is a gradient in electric field according to the Gauss law that you saw in JEE, only if there is a net charge inside a given region. So only if there is, I take some region like this, and you know what, let me annotate. If I take some region like this, and there is some gradient in the electric field which passes through this region, that means that there is some net charge inside this region. So if there is some gradient, you're going to get some net charge due to that. So this is the intuition for this, and this is why it's equivalent to the Gauss law that is there. And if you don't have any net charge, the net field coming in and going out is going to be the same, and so you're going to have zero on both sides of this equation. So that's just some intuition for this equation that I was trying to give. Uh, Finally, the point to stress is that using Gauss law and Shockley's equations, we can solve for any dynamics in the semiconductor. So with carrier density, which we saw last time, equilibrium carrier density, we are able to solve for the static like state of the semiconductor. Now we can solve for any dynamics as well. When you put electric fields, you put concentration gradients, whatever you want to do, you join materials together like you do in a diode. All of this can be solved by the equations that we derive over here. That's all I wanted to like bring to your attention. Finally, I have like asked ChatGPT to come up with some problem to summarize the concepts of this module as well as the solution. So it's a bit long to like show or share on the slides. So I'll share that with you on WhatsApp. You can go through that as well, which will just show you how to apply all these equations. And if you have any doubts with respect to that, you can reach out to me for that as well. Finally, the key takeaways from this module is that from both 3.3, which is this module, and 3.2, which is the last one, is very much important because everything in terms of designing devices is based on these two modules. Uh, Last thing that I want to say is that in these 3 weeks, we have explored all the physics that there is in terms of understanding the basics of semiconductor. In the fourth week, what we are going to do is we are going to use all of this to like basically like do the analysis of 3 devices. So the concepts or the building blocks have already been built. Now, as we end this course, we are going to analyze 3 devices: the diode, the MOS capacitor, and finally the MOSFET, which is what we were building up to from the beginning. So, in terms of learning the physics, we are pretty much done for the course. Now we are going to learn the application for the devices. So, like, I would encourage you to stick around for that module as well, because you will basically you'll be able to apply everything you've learned to the different devices. Yeah, so that's all for this module. Hope to see you guys in the next one.